Okay, oh, thank you. Today we are bringing together two things we learned. One thing was this idea of approximating polynomials, like Taylor and Maclaurin of polynomials, or the geometric power series. And the other thing is sequences and series, what we learned about convergence of series. And so we bring them together in this concept of power series. Okay, and I just want to remind you, a power series is a function that can be expressed as an infinite polynomial. So here's one example of a power series. If I were to write it out, it'd be a naught times x. Whoops. It'd be a naught plus a1x plus a2x squared plus dot dot dot. And what the a naught, a1, and a2 are, hey, it depends. You know, it depends on how crazy your power series is. Also, I want to remind you that this power series, you tell me, where is it centered?
Zero.
Yeah, this is centered at 0. You can also have power series that aren't centered at 0, that are centered somewhere else. Then it would be a sub n times x minus c to the n power. So you get a naught plus a1 times x minus c plus a2 times x minus c squared plus dot dot dot.
Mr. Shannon?
Yes,
We already have notes on convergence of power series.
that was what we did Friday.
Yeah,
What about that?
we did it.
Oh yeah, I'm just reminding you.
Oh.
I don't know, I'm doing an intro. It's like when you watch a show and they save scenes from previous episodes.
Oh.
I don't know, because this is only going to take me about a minute.
Sorry.
Yeah, just hold your horses. Okay, and so I do want to remind you that Taylor polynomials is just one example of what a naught, a1, and a2 can be. Right? Remember, with Taylor polynomials, a1 is f of c, a naught is f of c, a1 is f prime of c, a2 is f double prime of c over 2 factorial, a3 is f triple prime of c over 3 factorial. But that was just one example of what a naught, a1, and a2, etc. can be. They can be anything I want. Okay? And so now that I can have this infinity of power series, the question starts to be, okay, what values of x can I plug in such that I get a finite answer, that is, my power series is useful to me, and what values of x do I plug in such that I get infinity, which means the series is worthless to me, you know? And so there's a name for that range of x's that you can plug in that get you a finite answer. Do you remember what that range of x's is called?
Interval of convergence.
Thank you very much. Interval of convergence. So our big thing is to find what is the interval of convergence. What is the interval of convergence? And I want to remind you, there's actually only 3 possibilities for the interval of convergence of every power series in the whole universe. There's 3 possibilities. The first possibility is the interval of convergence is only at one point, only at x equals c, nowhere else. You plug in c and you get a naught, you plug in any other value for x in the whole universe and you get infinity. Well, that's not a very useful power series. The second possibility is that the interval of convergence is all real numbers. That is, you can plug in any value of x you care to, and you're going to get a convergent answer. That's very useful. A power series where I can plug in any x I want and not think about it is really nice. The third possibility is that the interval of convergence is only on an interval of x. Your interval of convergence is somewhere between a and b. And then we get this weird situation that sometimes it's between a and b, but it doesn't include a and b. Sometimes that interval of convergence is between a and b, and it includes both a and b. And sometimes, it'll include one of the endpoints, but not the other. Okay? It turns out that this ends up being the most interesting of the 3 scenarios, but I have to prepare you for all 3. But if I were to tell you about the AP exam, like 90% of the time, the interval of convergence ends up being an interval where you have to actually check the endpoints. And so this leaves us to the next thing we're going to do. So, Andrew, my little intro is over now. We're going to begin the episode. So, in the last episode, the hero died, but now we're going to discover they didn't really die. They're still alive. You know.
Oh, like Walking Dead.
That show's so lame. Oh, it's just snuff porn, Walking Dead. You can't kill zombies, they're already dead, so let's just kill them. Okay, alrighty, so here's the thing. So I need to do two things. Number one, I need to be able to find that interval. And number two, I need to be able to check the endpoints. And that's the two things we're going to do. We're going to find that interval by applying ratio test, and then we're going to check the endpoints to see which of those four scenarios we have, if it ends up being the third scenario. And so that's it. The rest of this period, all we're going to do is ratio test, check endpoints, ratio test, check endpoints. And so let me give you a million examples. Here comes the first one. Example number one, okay? I've got f of x equals, the sum as n goes from 0 to infinity, of n factorial times x to the n. Now, of course, I hope you know now, this is not Taylor and Maclaurin anymore. That's just one example of this infinity of different power series. And this is one of this infinity. So don't be giving me 2 factorial, 3 factorial in the denominators. Don't be doing that. Don't be giving me f prime, f double prime, f triple prime, because we're not that, you know, that's not what this is. This is a completely different scenario. If I plug in, I've got 1 plus x plus 2x squared plus 6x to the third plus 24x to the fourth plus ta ta ta. That's what that series looks like. How am I going to find the interval of convergence? What values of x am I allowed to plug in such that I get a finite answer? Now, yeah, the 0 is one value for sure. Can I plug in any other values? Could I plug in a half or a third or a hundredth? Well, let's find out. And the way we're going to find out is to do the ratio test. You're going to apply the ratio test. So I'm going to get the limit as n approaches infinity of the n plus 1th term over the nth term. Okay? But the thing is, I'm not doing this to find out if it converges or diverges. I want it to converge, right? I want interval of convergence. So now, I'm not going to use the ratio test to determine if it converges or diverges. I'm going to say, no, no, no. I want the values of x that make this converge. I'm going to set this ratio less than 1 and find out what values of x get that ratio to be less than 1. Because I want this to converge. Does that make sense to you guys? So unlike what you learned in section 10.7 of the Larson book, where you had to decide, is it less than 1? Is it greater than 1? No, we're setting it less than 1. I want this to converge. I want convergence. So I'm going to set it to be less than 1. But just like before, we're going to simplify. Okay, n plus 1 factorial over n factorial. Hope you guys get that that's n plus 1. X to the n over x, that's just x. Okay. If I want, I can take the absolute value of x out. So I get the absolute value of x times the limit as n approaches infinity of n plus 1. And I'm going to ask myself what values of x makes that true. Or you could leave it like this. Here's the point I want to make. What value of x makes this product less than 1?
Any fraction.
A fraction? Like a millionth? But could I choose an n big enough so that this term times a millionth would be greater than 1? Sure, a million. So how about x being a billionth? If x were a billionth, would this product be less than 1? No, because what would I choose my n to be? A billion. You see? Do you see that any x I choose, I can always find an n big enough so that this product is greater than 1? So you tell me, which of these 3 scenarios have I just found?
All.
Is it convergent for all? Can I plug in any x I like and have this be true? What values of x is this actually true for? Just 0 and nothing else. Any other x value I'd care to choose, I can find an n big enough so that this product is greater than 1. So do you see that this is true only for x equals 0? Any other x I choose, I can find an n big enough so that this product is greater than 1. I'll even write it on the board. Any other x I choose, I can find an n big enough to make the product greater than 1. So if this were an exam, your answer would be the interval of convergence is x equals 0. And that's it. Hey, let's do another problem. Like I say, all we're going to do is just ratio test over and over again. And then hopefully that'll prepare you for tonight's work. Example 2. I have a function which is expressed as a power series. It's, as n goes from 0 to infinity, of 3 times x minus 2 to the n power. That is, if I were to write this out, it'd be 3 plus 3 times x minus 2 plus 3 times x minus 2 squared plus dot dot dot. Again, no factorials. This isn't Taylor or Maclaurin.
Mr. Shane.
Yes.
So if you wanted to Taylor, you would just do the over n factorial, right?
Right. Exactly. In fact, my Taylor would have to look like this. It would be f, the nth derivative evaluated c over n factorial times x minus c to the n. Then if someone gave me a power series that looked like this, I'd be going, oh, that's the Taylor, or in fact, yeah, that's the Taylor power series.
That makes so much more sense.
Okay, so hey, and you know what we're going to do? Let's do ratio test. Limit as n approaches infinity. The n plus 1th term is 3 times x minus 2 to the n plus 1. Remember, you're not augmenting x. You're only augmenting n. Only n gets increased. The x just stays the same. And we're going to set that less than 1 because we want this to converge. Are you guys okay that I get the limit as n approaches infinity of just x minus 2? Everything else canceled. So, are you okay that I don't need that anymore because I got no more n's? I don't care that n goes to infinity, I got no n's. And finally, are you aware that when you have an absolute value inequality where it's less than, you can rewrite it like this? Are you guys okay with that? Just get the opposite of this guy, put it there, and whatever that symbol is, put it there. So I'm going to add 2 to every single quantity, and I get 1 less than x, less than 3. So do you see this is the third scenario?
Yes.
But I want to remind you, the third scenario says this. Or. And you've got to decide which of these it is. You've got to check the endpoints. Well, you know what I'm going to do? I'm going to check the endpoints by literally plugging them into the original equation, okay? So here's the process of checking the endpoints, and this ends up being the reason why you learned all of that stuff about convergence of series from that little handout I gave you, so you can check the endpoints. Let's try f of 1. We're going to try f of 1, and I'm going to stick 1 into this guy here. Right? There's nothing complicated. I'm just sticking a 1 in for every x. So f of 1 ends up being 3 minus 3 plus 3 minus 3 plus 3. Okay? If you prefer going term by term, some of you may prefer to just stick 1 in there. So you get the sum as n goes from 0 to infinity of 3 times negative 1 to the n power. You can either think of it term by term, or you can just plug into the original. Both are the same. It's just up to you. It's what you prefer. If you're the type of guy who likes to think deductively and look at the terms, then plug in and do that. But if you're the type of guy who likes to just look at the general term and make the determination based on the general term, do that. But either way, tell me, does this guy converge or diverge?
Diverges.
It diverges, because this is a geometric series whose r is, not in between negative 1 and 1. This is a geometric series whose r is less than, less than or equal to negative 1. So this is a divergent geometric series, Or if you do it this way, then you can just observe, oh, look at that. It doesn't equal anything in particular. 3 minus 3 plus 3 minus 3 plus 3 doesn't have any particular answer. So it diverges. Which means I don't get to have that endpoint. How about that endpoint? Let's try f of 3. Well, f of 3 is going to be 3 plus 3 plus 3 plus 3 plus 3 when I stick in a 3 for every x. Or f of 3 is going to be the sum as n goes from 0 to infinity of 3 times 1 to the n. Either way, I hope you see that this is a divergent geometric series also. So I don't get to have either endpoint. Neither endpoint works. And so you end up with just this answer. Now, me personally, I prefer expressing the answer that way, but our textbook and quite often the AP exam have an alternate way of expressing the answer. They do this. They go, imagine, I've got my number line, and the interval of convergence is centered at 2, and it goes as far to the left as 1, but it doesn't include 1, and it goes as far to the right as 3, and it doesn't include 3. So they'll actually say, oh, my interval of convergence, it's centered at 2 with a radius of 1. They're like picturing 2 as the center, and then it's like a circle or something. I don't know what they're saying. But anyway, you'd say the interval of convergence has a radius of 1. So the book and the AP exam, sometimes they won't ask you for the interval of convergence. They'll just ask for the radius of convergence. And in this case, the radius of convergence is 1. Because you have a convergence centered at 2 and 1 on either side, yes?
If you say it like that, how do they know that you aren't including the endpoints?
You don't know. You don't know. Yeah, so that's their tricky way of asking you to do the ratio test part without having to actually do the endpoint part. Yeah, isn't that weird? I know, so that's my beef with them. I think it's really dumb, but whatever. Yes?
So if you find that your endpoints converge, then your interval of convergence changes?
Yes, the interval of convergence changes, but the radius of convergence wouldn't. Because only the ratio test gets you the ratio test gets you the radius of convergence, but checking the endpoints tells you if the endpoints converge. So it's weird. So you can get radius of convergence without checking the endpoints. Hey guys, I got to show you one more thing, and then I'll send you on your merry way and hope that it makes sense to you. Here, Here's example number 3. Alrighty. Let's say I've got a function that's the sum as n goes from 0 to infinity of -1 to the n power times x to the 2n plus 1 over 2n plus 1 factorial. Alrighty. If I want to write these out, this is going to get me x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over some factorial, etc. Anyone recognize what this is actually a power series of? Not cosine. Sine, yeah. Sine of x. So let's find the interval of convergence. Here it comes. I'm going to do ratio test. And if the bell rings, could you hang out just till we're done? I'm so sorry. So I got -1 to the n plus 1. I've got x to the 2 times n plus 1 over 2 times n plus 1 factorial, all over -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And I'm going to set this whole big thing less than 1. Thanks, Fatima. Next, I'm going to divide by the or rather multiply by the exponent. So I got the limit as n approaches infinity of -1 to the n plus 1. So this is going to be -1 to the n. Oops, don't go yet. X to the 2n plus 3 over x to the 2n plus 1. And then I've got 2n plus 1 factorial over 2n plus 3 factorial. And all this stuff has to be less than 1. Now I'm going to factor, or rather I'm going to cancel. And I hope you see that the negative ones go away because it's just an absolute value anyway. And I end up with x squared on the top. And on the bottom, I'll tell you why tomorrow, but you end up with 2n plus 2 times 2n plus 3. And that's got to be less than 1. 2n plus 1 factorial over 2n plus 3 factorial, you've got 2 extra terms on the bottom, the 2n plus 2 and the 2n plus 3. And I'll tell you why tomorrow. I'm so sorry for keeping you. And here's the last thing. What values of x is this going to converge for?
All values.
Yeah, how do you know?
Because the denominator is infinity.
Thank you. Any particular value of x I plug in, I can find a value of n that makes this less than 1. Even if I plug in a billion for x, I'll just choose a trillion for n. You see what I mean? So yeah, this is converges for all x. So this is that second scenario. All right, hey, good luck on tonight's homework. Test the endpoints, 3738 or geometric power series. Good luck, and we'll do it tomorrow, man. We'll do it tomorrow. 1950.